It all started with a single apple. Oh, almost forgot. And a curious mind. Long before that moment, ancient thinkers like Aristotle believed that everything in the universe is naturally drawn toward the center of the earth. Which, if you think about it, was kind of true, but not quite. Anyways, let's go back to the apple thingy. There he was, Isaac Newton, just sitting under an apple tree, probably thinking about life, when suddenly, boom! An apple falls right in front of him. Newton asked the big question. Why?
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 Why does it always fall down? Why not sideways? Why not up? So many whys that eventually led to one of the greatest discoveries in science, the gravity.
And those same questions bring us to our topic today, which is the gravitational laws and centripetal motion. So the following are our objectives.
So let's start off with Newton's law of gravitation. Quick recap, gravity is a natural force of attraction between all objects that have mass. So take note, all objects that have mass have gravity. So in a concept of a falling apple, both the earth and the apple was exerting force in the same magnitude but in opposite direction. But why do we see it as if the earth is pulling the apple when in fact both of them exerts force on the same magnitude, though in opposite direction? Well, they have different masses, which means they have different acceleration. So, the apple, mas gamay iyang mass, so mas fast siya mo accelerate. That's why we see it as if the earth is pulling the apple. It was in the year 1687 when Isaac Newton published his universal law of gravitation, which in a word states that every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of the masses of the particles and inversely proportional to the square of the distance between them. Or in symbol, we have f of g is equal to g times m sub 1 times m sub 2 all over r squared, which the g here, or the gravitational constant, serves as a placeholder. So wala pa siya exact value during the time nga na-establish ang law of gravitation. So, a century later, or in the year 1798, naanay value ang g. So, it was determined by Henry Cavendish through his experiment, which is called the Cavendish experiment. So we now have the value of our g, which is 6.67 times 10 raised to the power of negative 11 Newton meter squared per kilogram squared. So in the formula of the law of gravitation, f of g stands for the gravitational force, m1 and m2 stands for the masses of the object, and r is the distance between them, and the g is our gravitational constant, which has a fixed value of 6.67 times 10 to the power of negative 11 Newton meter squared per kilogram squared. So let's have a look at this illustration presented on the screen. So the gravitational force simply measures the attraction between the two objects. So object 1 and object 2. So ang gina-measure sa gravitational force is the attraction between sa ilahang duha. Based sa formula, gravitational force is directly proportional to the masses of the object, which means if greater ang masses, or pag mas bugat ang katong mga objects, it also means na mas dako or mas greater ang iyahang gravitational force, whereas it is inversely proportional to the distance or the r. So pag mas lagyo ang duha ka object, mas muhinay or mas gamay ang ilahang gravitational force. So if the object is duol or nasa earth, the small r squared will now become a capital R sub e squared, which means it stands for the value or the constant value sa radius of the Earth. Kay mao na siya ang distance nga atong gamiton. And the M1 would now become M sub E, and the other M, or the M2, is the mass of the object. So M sub E stands for the constant value of the mass of the Earth. Pero if layo ka sa Earth, then let's use the original formula nga small letter R. So from the formula of gravitational force, or the law of gravitation, ma-derive nato ang value sa free fall acceleration, or acceleration due to gravity, which on Earth is 9.8 meter per second squared.
So we have here the formula for the gravitational force, which can also be written as, since nara siya sa Earth, and let's identify the given values, which is the mass of the Earth and the radius of the Earth. The F of G can also be written as MAG, or mass times acceleration due to gravity, and we can cancel out M for both sides, and that will give us the formula for acceleration due to gravity. Since we now have the formula, which is G times M of V over RE squared, we can now substitute the given values and solve for our acceleration due to gravity. And we can cancel out the units as well. So that will give us 9.8 meter per second squared. We end up with the unit meter per second squared because we can also write Newton as kilogram meter per second squared, which will cancel the unit kilogram. And that's it.
So let's see how it's done. So now let's try to solve some example or problems here. So the mass M1 of one of the small sphere of a Cavendish balance is 0.0100 kilograms. The mass of M2 of the nearest largest sphere is 0.500 kilograms, and the center-to-center distance between them is 0.0500 meters. Find the gravitational force F of G on each sphere due to the other. So let's do it step by step.
For first example, let's just write the formula for gravitational force and then identify the given. And then we can substitute the given value sa atong formula and cancel out ang mga necessary i-cancel na mga units. And we have our final answer.
So for the second example here, or second problem, suppose the two spheres in the example 1 are placed with their centers 0.0500 meters apart at a point in a space far removed from all other bodies. What is the magnitude of the acceleration of each relative to an inertial system? Now on a third problem, a robotic lander with an Earth weight of 3,430 Newton is sent to Mars, which has a radius of r sub m equals to 3.40 times 10 raised to 6 meters, and mass m sub m, which is 6.42 times 10 raised to the power of 23 kilograms. Find the weight F of G of the lander on the Martian surface and the acceleration due to the gravity, or the G of m.
To get the acceleration for both objects, we can rearrange the force equals mass times acceleration, which will give us force divided by the mass. Plugging in the values, for A1 we have the answer, and for A2 we follow the same procedure. For the third example, let's plug in first the given. We have the F of G na nasolve na to ganina, and or the weight, and then the Rm, which is the distance, and the M of M, or the mass of Mars, and our constant G. And as well, the acceleration due to gravity is Earth. So we have here the formula in words. Gravitational field is defined as equal to the universal gravitational constant G times the object's mass divided by the square of the distance from the object's center or the R. The direction is toward the mass's center. In symbols, we have G is equal to capital G multiplied by capital M all over R squared, where G is our universal gravitational constant, which we talked about kaganina, and the M is the source of mass. It can be Earth, Moon, satellites, and etc. And the R, just like kaganina, it's the distance of it's the distance between the center. So as you can see here, formula sa gravitational field is derived from the formula of gravitational force or the universal gravitation. So remember the second law of motion, which is force equals to mass times acceleration, or we can write it as it involves gravity. F of G is equal to m times a of G. So F of G is what we know as the universal gravitation. So that's equal to constant G mass 1 times mass 2 all over the distance, and copy the m times a of ag. Now let's talk about the vector form, or why is it negative. So negative only tells us the direction because it indicates that the field points toward the center of the earth. So diba ang gravity is pulling mo na siya. So it's just the direction of the force nga padulong siya or bound to the earth. So let's jump right into another topic, which is the gravitational potential energy. So we know that the gravitational potential energy, the formula is mgh, where m is the mass of the object, g is the acceleration due to gravity, and h is the height of the ground. So this formula only works pag naka sa surface of the earth because the gravity is constant. Pero pag mulayo na ka sa surface of the earth, the gravity is not constant anymore and it gets weaker, so therefore dili na accurate ang kanina formula. So we'll use the general formula for gravitational potential energy, where PE or potential energy is equal to the negative capital G multiplied by the capital M sub E times small letter m all over R, which G, or the capital G, stands for the gravitational constant, M sub E is the mass of the earth, and a small letter m stands for the mass of the object, where M sub E and R sub E are the mass and the radius of the earth respectively. So if the object moves away, the PE increases, which means it becomes less negative. Wherein if the object falls down toward the earth, the PE decreases, which means it becomes more negative. So let's have the formula for the change in potential energy. So change in potential energy is equal to the potential energy final minus the potential energy initial, or this one. And for any conservative force like gravity, the rule is, so diba, energy hindi siya mawala, it can be broken down, pero matransfer siya or matransform siya into another form of energy. So that's why change in potential energy is equal to the negative force, or we have here the force is equal to the negative change in potential energy. It's because pag mag-lose ang potential energy, ma-add to siya into kinetic energy, which can be the force. So that's why ang changes sa potential energy dili siya mawala but matransform into the unit of force or the kinetic energy. So let's try to solve this example. Just pause the video because it's so long. Hindi ako siya basahon. Let's proceed to the solution. So now let's proceed to the orbital motion. So that is defined as how objects like planets or satellites move in a circular or elliptical path because of gravity. So the best example for this is the moon that orbits the Earth. So that's natural. And we also have the artificial satellites that are man-made. So how does this happen? Di unsa man pag orbit sa satellite, nganong dili man siya mahulog if the Earth has a gravity, di ba? It happens because as the gravity pulls the satellite toward the center, the satellite's forward motion keeps it moving around instead of falling straight down. So, as we know, the centripetal force happens if an object undergoes a circular motion. So, by this analogy, we can say that the centripetal force, ang iyang orbit, pag-orbit niya sa planet or other celestial bodies is due to the gravitational force. So, by that, we can use that expression to derive the formula of orbital velocity. So, a satellite must move at the right speed. If hinay kaya siya, it will fall back to Earth. If kusog ra po kaya siya, it will escape the Earth's gravity. So, it shows here kung giunsa pag-derive ang orbital velocity. So, we can equate the gravitational force and the centripetal force. Substituting their respective formulas, we have G times m of p times small m over r squared is equal to mv squared over r squared. So we can cancel m both sides. So that will give us gm sub e over r squared is equal to v squared. So para makancel ang squared, so ato siyang square root both sides. Then this is our final formula. Square root of g sub e over r is equal to v, or the orbital velocity. So orbital period. So the orbital period is the time that it takes for one full revolution around the Earth. So the distance for one orbit is the circumference, which is the 2 pi r. And the time for one revolution is t is equal to 2 pi r over v, which is the velocity, which is equal to 2 pi r 3 raised to 3 halves divided by the square root of g m sub v. So let's also discuss the total mechanical energy a bit, because we'll have problems about this later on. So the total energy is the sum of kinetic and the potential energy. So in symbol, that is E, or the mechanical energy, is equal to Ke plus Pe. So substituting the value and simplifying it, we get the total energy is negative, meaning the satellite is gravitationally bound to Earth. So its value is half of the potential energy and is negative. So now it's time for some problems to solve.
Johannes Kepler, a German astronomer, formulated 3 fundamental laws that describe planetary motion. His discoveries helped bridge the work of earlier astronomers like Copernicus with the physics later explained by Isaac Newton. Kepler's first law, also known as the law of ellipses, states that planets move in elliptical orbits with the Sun as one of the foci. In other words, a planet's path around the Sun is not a perfect circle, but an elongated oval called an ellipse. The figure here shows two focus points, labeled F1 and F2. Every point on the ellipse has the same total distance from these two foci. The major axis measures the longest distance across the ellipse, while the minor axis measures the shortest. Kepler's second law, or the law of equal areas, states that a planet covers equal areas in equal intervals of time. For example, in the diagram, the shaded areas between points A, B, and the Sun, and between C, D, and the Sun, are equal. This shows that during the same amount of time, the planet sweeps out equal areas, even though it travels different distances. This law beautifully demonstrates that the planet's speed changes as it orbits the Sun, fastest at perihelion and slowest at aphelion. Kepler's third law, known as the law of harmonies, states that the square of a planet's orbital period is proportional to the cube of the length of its semi-major axis. In simpler terms, planets that are farther from the Sun take much longer to complete one orbit than those that are closer. This relationship shows the balance between a planet's distance from the Sun and the time it takes to revolve around it. For instance, Earth takes 1 year to orbit the Sun, while Jupiter, which is much farther away, takes almost 12 years. This law reveals the precise mathematical harmony of the solar system.
The force that keeps the Earth going around the Sun is gravity. Isaac Newton developed the law of universal gravitation, which explains the unseen force behind Kepler's third law. This law was crucial in understanding the motion of planets in our solar system. So, Newton described motion using 3 main ideas. First, position. Position describes where an object is at different times. Position is where an object is located at a certain time. For example, the Earth's orbit can be described by its position at various times during the year. Second, velocity. Velocity is a change of position with time. So velocity always has magnitude or speed and direction. For example, a car moving 60 km per hour north has a velocity of 60 km per hour north. Third, acceleration. Acceleration is the rate of change of velocity. It shows how fast the velocity changes. For example, when a car speeds up, slows down, or turns, it accelerates. In circular motion, acceleration always points toward the center of the circle. This is called centripetal acceleration.
Circular motion. During circular motion, the centripetal force has a constant magnitude. In symbol, F equals centripetal force, and m equals mass of the object going in a circle. V equals object's velocity. R equals radius of circular curve. AC equals centripetal acceleration. The universal law of gravitation is usually stated as an equation, where phi is the attractive gravitational force between two objects of mass n and m2 separated by a distance r. The constant g in the equation is called the universal constant of gravitation. Newton's great step was developing this law and using it, with his laws of motion, to explain the motion of lots of different things from falling objects to planets. Amazingly, out of these simple and general rules, Newton was able to show that all of Kepler's descriptive laws for orbits followed as a direct consequence. When you combine Newton's gravitation and circular acceleration, which must balance in order for the object to remain in orbit, you get a nice relation between the period, distance, and mass of the central body. It beings by equating the centripetal force sent due to the circular motion to the gravitational force. It beings by equating the centripetal force sent due to the circular motion to the gravitational force. Let the Earth be m1, and the Moon be m2. For circular motion, the distance r is the semi-major axis A. The orbital velocity of the Moon can be described as distance, time, or circumference of the circular orbit divided by the orbital period. So setting the forces equal yields, note that the m2 will cancel, so that circular orbital motion is independent of the mass of the orbiting body, which we rearrange to place all the a terms on the right and all the p terms on the left, which should look startlingly like Kepler's third law, but this time for the Earth's mass or any other instead of the Sun's mass. To use ANT to solve for mass, manipulate once more so that
First is determine the gravitational force between a 60 kg and a 70 kg person who are both standing 2.0 meter apart. So the first given is m sub 1 is equals to 60 kg, the m sub 2 is 70 kg, and the distance to the r is 2.0 meter. So we will find the gravitational force, or the F sub g. So the solution of finding the F sub g is F sub g equals g times m sub 1 times m sub 2 over d squared. So we will substitute the given. So it is the value of the g, which is the constant. The gravitational constant is 6.67 times 10 raised to negative 11 Newton times meter squared per kilogram squared times our m sub 1, which is 60 kilogram, times our m sub 2, which is 70 kilogram, over 2.0 meters squared. So it is equals to 28,014 times 10 raised to negative 11 Newton times meter squared over 4 meters squared. So our total gravitational force is equals to 7.0035 times 10 raised to negative 8 Newton. So the second problem is a sales lady whose mass is 52 kg is doing a product demonstration in front of customers. She exerts a gravitational force of 7.45 times 10 raised to negative 8 Newton on a 57 kg woman who is standing in the front row. How far is the woman from the sales lady? So the given are F sub g is equals to 7.45 times 10 raised to negative 8 Newton. The m sub 1 is 52 kg. The m sub 2 is 57 kg. So we will find the d, or the distance. So the solution in finding the distance is d is equals to square root of g times m sub 1 times m sub 2 over f sub g. So we will substitute the given in the solution. So the g is 6.67 times 10 raised to negative 11 Newton times meter squared per kilogram squared. Our m sub 1 is 52 kg and our m sub 2 is 57 kg over our f sub g is 7.45 times 10 raised to negative 8 Newton. So if we will calculate all of that, we will get an answer of 1.62 meters. So our distance is 1.62 meters.